So good afternoon, everyone, and welcome to the Traffic Engineering with Segment Routing session for today. My name is Leonir Hoxha. I'm a network consulting engineer within Cisco for a couple of years now, based in Poland, in Krakow. So I was dealing with data center customers, enterprises, and the last years mostly with service provider. That's why the focus today will be on traffic engineering within a service provider environment, all right? The assumption is that you have at least some knowledge on MPLS networks, right? On a traditional MPLS forwarding plane at least, because I won't cover in depth the segment routing. So I will go with traffic engineering mostly, right? But anyway, I will cover briefly as well segment routing, at least the building blocks of segment routing, all right? Okay. So this is the agenda. Briefly, I will go as I said in the beginning. For those who don't know about segment routing or haven't heard before, we will see the building blocks of segment routing. After that, we will cover the segment routing with traffic engineering. Specifically, we will go a little bit with the disjoint paths and L3 VPN, which are the use cases which are used mostly by service providers today. So what is segment routing is the question, right? So segment routing is basically MPLS, okay? The only change is now at the control plane level, right? Because at the data plane, we still use MPLS labels. So what happens is now at the control level, at the control plane level, we introduce SR. So we have some sort of set of extensions on the IGP level, right? So in case of ISIS, it would be the TLVs. So we have some extra TLVs. And in case of OSPF, then we have the OPAC LSA as an additional attribute which advertises the so-called segment IDs for the segment routing, okay? So segment routing is basically, so the source is basically choosing the path to reach the destination, right? That's different from what we see in the traditional networks where we have destination-based forwarding. Now with segment routing, we are able to do source-based routing, right? So the source can be different things here. It can be the edge device, the provider edge, can be a VM sitting somewhere behind in your data center, or can be an application as well, sitting behind your data center. The only thing is that the VM or the application need to understand segment routing, right? So what is now a segment? Yeah, so the segment, the source routing, basically segment routing means, right, the source chooses the path and encodes that path on this on a packet header, basically, right? That packet header then has an ordered list of segments. So there is a list of segments. It's simply like a label stack in MPLS, right? You have many labels in a stack. Here we have an ordered list of segment or segment IDs. Now, what is a segment ID? It's just an identifier. It's a value similar to a label, right? And it can have two different meanings. It can have it can mean a forwarding instruction or a service instruction. From a forwarding instruction, it can mean something like some sort of traffic engineering within your SP or data center. Or a service instruction means you have some sort of firewall or a load balancer, and you have a source and a destination. Now, before the packet goes to the destination, you want to go first to the firewall, do whatever you want to do in the firewall, and then forward it back to the destination. Yeah. As I said, we still use the MPLS data plane. From the forwarding plane point of view, we still use MPLS. There is no changes here. The only flexibility is now that you can use MPLS or IPv6 at the data plane, okay? So what it means is, in case of MPLS, you will have the traditional label stacks. I mean, the labels in a stack. In IPv6 case, it means, I would say enterprises would mostly benefit from this because in enterprise customers, mostly you won't see MPLS enabled, right? So you will have maybe IPv6. So if you have an infrastructure with IPv6, you can still use segment routing and do some sort of traffic engineering, right? And we still use the same operations as in MPLS, right? So there are this push, continue, and next, right? So imposing, swapping, and popping the label at the end. So we have two types of segments. There is two types of segment. When I say it's more from the significance point of view. What I mean with this is that the global segments, it means that all the devices in your domain, in your network, need to understand the segment, right? So they need to understand what that value means, okay? And this is a unique value in your network domain. The local segments have local significance, meaning only I understand what it means, because because that value is only for me. And we will see later on why this is the case, okay? So the global segments, they are being distributed by the IGP, ISIS or OSPF, right? There is this notion of sRGB in segment routing. That's the segment routing global block. That's basically the same thing as a label range in MPLS, right? You have the range of labels which can be assigned to a specific prefix, and then you distribute this with an LDP or RSVP. Doesn't matter. The only difference is now that you don't need to LDP or RSVP here. You do it with the IGP only, right? With that extension only. And that sRGB, as I said, is a pool of segment IDs which are distributed by the nodes within the same domain, okay? Now we have the sRGB plus index. What it means is basically this. The sRGB starts from 16,000, right? The range of values, and goes up to 23,999. So once you enable segment routing in your domain, right, in your IGP domain, all of the nodes and routers will start distribute that prefix segment IDs, right? And those segment IDs, as I said, are part of that sRGB block, yeah? Now, how this is being advertised is in this way. You can simply say, advertise the block plus an index number. That index number is a unique label value per domain, per node, sorry, right? So you are advertising sRGB plus index. So 16,000 plus, if the index is 1, you assign number 1. It means 16,001. You assign for an interface loopback, for example, of one of the devices in your network. And this should be a unique value, right? So the recommendation is that, let's say you have an environment where you have many vendors, not only a single vendor, right? So the recommendation is to use the same sRGB value within all your different vendor devices, right? So this is the first type of segment IT, and I would say this is the most important one, right? That's the prefix segment, or the node segment ID. What it means is it's a label value assigned to a unique, assigned to a specific node, and this is a unique value. Now, what we mean by unique value is simply like you assign an interface loopback which identifies your device, right? And that's IP address, for example, is unique within your network because you know, okay, this IP belongs to that device because this is part of the interface loopback, right? Same case here, the node segment should be unique value, right? And you assign per device only on one interface loopback on the IGP level, the segment ID, right? Part of that sRGB block, yeah? So what it means is now, for example, all the nodes in that small topology here will have a unique value, unique node segment ID, right? Now then, there is the second type of segment ID, which is the adjacency segment ID. The adjacency segment ID is now, as I said, this is that local significant type of segment ID, right? If, for example, node C assigns a adjacency segment ID of whatever value, it will advertise to node O, B, and D, but all the rest of the devices will ignore that, right? Because that's not for them. the only thing or the only label value or segment ID that all the devices in your network should understand and accept and install in the forwarding table is the node segment ID. Okay? So that's the node segment ID, as I mentioned. It's part of the, so the labels are assigned from the sRGB block, right? And this is an example. For example, here we have a packet that is sourced from the left-hand side, node A, that goes to the destination, node Z, right? So what happens is that that node segment ID is 16,065, right? This is assigned on node D. So this is the interface loopback on node D, okay? So all of the rest of the devices, they know that segment ID belongs to node D. And if I want to send a packet behind node D, meaning node Z in this case, which is a destination, then the top label on my packet would be 16,065. And all of the rest of the devices in the network, they know what that value means, so they know how to forward that packet to reach the destination. Okay? The other good thing is that now with segment routing, you can also have do some sort of equal cost forwarding, right? You have some, let's say, ECMP paths. You have different 2-3 links to go to the destination, right? Only using that node segment ID on top of the packet, you can simply do ECMP path forwarding, ECMP-based forwarding. It can be ISIS or SPF, doesn't matter. As long as each of the devices have a unique value, then by default, it will forward based on ECMP paths. Adjacency segment ID, that's a second type, which I said, right? Which I mentioned before. Here we have an example. Node C advertises a adjacency segment ID of 29,003, right? What happens is now node O, he sees that value, but he will not install it in the forwarding table, in the LFIB in this case, right? Only node C will install it by his own LFIB because it's locally significant, right? Here is an example where we can use both segment IDs, right? The node segment ID and the adjacency segment ID. This is a good example of doing some sort of traffic engineering, right? Because you can say, for example, we have a packet going to node 5, right? Behind node 5. And that packet is sourced somewhere behind node 1, right? So the first label is that 24045, right? That's the bottom label, or the bottom segment ID. This is the adjacency segment ID of node 4 going to node 5. Okay, that's the directly connected link to node 5 from node 4. Why? We will see now. And then the second label, or the second segment ID, is 16,004, which is the node segment ID of node 4, right? So what happens is we say at node 1, go first to node 4 to reach node 5. Now, reaching node 4, it doesn't matter which way you go. As long as you can reach it, just go there first, right? In this case, it will use ECMP paths, right? So it has 2 paths, through node 2 and through node 3. So reaching node 4, it will go through two paths. Once it reaches to node 4 will see, okay, what is the top label? It's 16,004, means it's me, right? So I will pop it. And then the next label is what? 24045. It means it's my adjacency segment ID assigned to that link going to node 5 in this case, right? And then it will just forward that packet through that link, yeah? So this is a good example of doing some sort of explicit path traffic engineering, right? Even if you have 2-3 links, you can say just use that link with adjacency segment ID, or you can say use some loose path just with a node segment ID, okay? So this was just a repetition of segment routing building blocks, right? So now we're gonna go with the segment routing traffic engineering. This is a high-level architecture. This is how it looks like. For example, you want to achieve some sort of traffic engineering with segment routing, right? You have 3 different domains, right? We have area area Y, X, and Z, right? On top of that, we have a PCE controller. Now that's a controller which is external to your network, but that is connected to your network, that is somehow talking to the network devices, right? Now, the controller has two types of databases in this case. It has the TED database and LSP database, right? The TED database is basically the whole IGP, let's say, prefixes which you have in the domains, in each of the domains, right? The LSPDB database is the LSPs that are created now, like the traffic engineering LSPs, based on requests, right? So how does now the question is, how does the controller know what we have down in the network? This example here is something like this. So we have at the left-hand side a PCC. What is a PCC? A PCC is a path computation client. It can be any device in the network, a router or a switch, right? A PCE now is a path computation element. This is the controller, okay? Now there are different types of messages that are being forwarded between the controller and the network device, right? So there is the PSEP request, right? That goes from the PCC or the network device to the controller to request some path or whatever, right? Then there is the PSEP reply that goes from the controller to the network device, right? Then you have the PCC report. PCC report means if I've installed a new LSP, now I need to report the controller to say, hey, I have a new path installed on my LFIP. Now I want to let you know what I have, right? That's an update, the report. And then the PCE controller replies with a PCE update saying, okay, I understood you. Now I keep state of that LSP, okay? And the last message is the PCE initiate. That means when the controller comes up with a new calculation and goes down to the edge device and says, hey, go and install a new LSP, for example, a pseudo wire, doesn't matter what, right? Now that's PCEP, that's a new protocol. Actually, it's not a new protocol, it's an old protocol, but lately it has been used a lot, right? Especially when it comes to the SDN and all this stuff, right? Now there are two different protocols here that PCE talks to the network devices in order to install new paths, right? There's the BGP-LS or BGP link state. Now what it means is that with BGP link state, let's say at least one device at each of the domains redistributes the IGP database to BGP and forwards that database via BGP-LS to the controller. Now the controller knows exactly what you have in the network because it has the whole IGP database. So it has the visibility of what you have in the network running down, right? And so that's how you have the visibility at the PCE level, right? Now the PCEP, that's on the left side there, right? That's the protocol that the controller talks to the device now back and saying, let's say if he needs to initiate a new LSP, he talks with the PSEP, right? So we get the visibility with BGP-LS, and then we install new instruction with PSEP downwards, right? A binding seed. Now, what is a binding seed? A binding seed in SR represents a tunnel, right? A traffic engineering tunnel, as an example. Now, you might ask why we need a binding seed now. Okay, we can do this even simply with prefix segment IDs, node segment IDs, that's fine. But sometimes you might hit some hardware limitation, software limitation that you can't have in a label stack more than 5, 10, 20, whatever labels, right? And the binding seed can help you out. Now here, what it means that a binding seed can represent more than one segment ID or more than one MPLS label. So this is an example here. The one head end, for example, now he has an LSP to AC1 on the right side, okay? And so he goes to he sends a PCC report to the controller and say, hey, I have a binding seed assigned to the 3 segment IDs, 17,002, 3, and 4, And that binding seed 4001 represents these 3 segment IDs. So instead of using now 3 labels, we use only 1. Okay? And so he reports to the controller. Okay? Now comes a request from a top of rack, for example, device on the left-hand side from within your data center. He needs to reach the AC1 on the other side, right? So he goes to the controller and say, hey, I need to reach AC1. Please tell me or give me a path or a list of segment IDs on how I can reach that AC1. Yeah? And the controller comes back then and says, okay, to reach AC1 first, you need to go to the 1 head end. Yeah? That's the exit point from the data center. And to reach 1 head end, you need to go. You need to use 17,001. That's the node segment ID of 1 head end, right? And the second segment ID is that binding seed. So you see now, on the Tor, we have only 2 segment IDs or only 2 labels to reach the destination instead of having 4 or 5 of them, right? So once the packet reaches 1 head end, now the 1 head end will see, okay, the top label is 4001, which means it's the binding seed, and I know what it means for me because I assigned that. It means I need to forward traffic on that particular tunnel, yeah? And that's how it looks like, the forwarding then. Now here we have an introduction of the service orchestrator, right? Why we need a service orchestrator? That basically, it's in the SDN world, right? You want to automate stuff, orchestrate, adding new services, not doing it anymore manually, but doing it automatically, right? So what happens is now you have, again, 3 different domains. All of them run ISIS as an IGP. However, you don't have visibility between those domains, so you don't do any sort of redistribution, right? So if Tor1 wants to talk to AC1, he cannot do it because there is no visibility at all, right? So the PCE now collects the topology by a BGP LS, as we said, right? And the service orchestrator now, for example, an application or a new customer comes and says, you know, I need a new service, and you go to the service orchestrator and say, okay, I want a new service. The service orchestrator now goes down to the edge device, in this case, the top of rack device, right? Using some Yang models, right, in XML format, and says, hey, go and create a new pseudo wire. In this case, pseudo wire 123 that goes from Tor1 to AC1, okay? And that now that Tor1 device will say, okay, I have a new request for a new service, right? And he will ask himself, do I have an LSP to reach AC1? Yeah? If yes, then okay, he will just forward it based on that LSP. If not, which is in our case, he will go now to the controller and say, hey, I have a new request for a new service, but I don't know how to reach AC1. Yeah? And so the controller will say, okay, I have a path for you since I have the visibility from all these 3 domains, right? DC, WAN, and access. This is the label stack or a ordered list of segment IDs, which you need to use in order to reach the destination, which is behind somewhere AC1. Yeah. And so then the reply comes down and it says, this is the explicit routing object, ERO. So first label stack is 18001, which is the Anycast SID of ABR1 and ABR2. Now this is an interesting case. Why? Because we have 2 exit points, right? We have ABR1 and ABR2. From Tor1 point of view now, if he assigns the first segment ID, the Anycast SID, which is the same on both devices, which is 18001, he will reach the closest device to himself, right? He will check the IGP table, so the routing table in this case, and will say which device, in this case ABR1 or ABR2, which one of them is more closer in order to exit my domain. And in this case, he will say, okay, ABR1 is closer to me, so in this case, I will use Anycast SID, which will reach ABR1, okay? Once that packet reaches ABR1, the second segment ID is 18002. Again, it's Anycast SID of ABR3 and 4 now. this is the exit point of the one domain, right? And again, the ABR1 will calculate now which of these two exit points is closest to me from the cost point of view, okay? And he will say, okay, ABR3 in this case is closer, so I will just forward that packet through ABR3. And once the packet reaches ABR3, which is the exit point from one domain, now ABR3 has visibility at the access domain, right? And he will just forward based on unicast SID 16001, which is basically the node segment ID of AC1, okay? And that's how it looks like from the segment IDs or the label, MPLS label point of view, the forwarding, okay? Now we have, that's another case, or the second case, on-demand next hop with a policy, right? Here we have two TORs, TOR1 and TOR2, which want to, for example, go to AC1 and AC2, right? So the source is at the TORs, and the destination is at AC1 and 2. The service orchestrator goes down to both of them, to TOR1 and TOR2, and says, hey, create two pseudo-wires, but these two pseudo-wires should have disjoint path, meaning none of these two paths should, let's say, touch each other, right? It should be a disjoint path. It can be in a case, for example, you have an active and backup pseudo-wires, which you want to have different paths always, right? And so the service orchestrator goes down, and the edge device says, create two pseudo-wires with this specific policy, meaning disjoint paths, right? What they will do is normal. They will go to PCE controller and say, calculate a path for me, both TOR1 and TOR2, which should be disjoint, right? And so the PCE controller, since he has the visibility from all the domains, he will go and calculate a unique path for TOR1 and a unique path for TOR2. In this case, this is a disjoint path for both of them, okay? And so at the end, this is how it will look like from the forwarding point of view, right? TOR1 will have different segment IDs. Now we will not use anymore the anycast segment, anycast SIDs, right? Because now we need to have a specific node segment ID, because we do some sort of explicit traffic engineering because of that disjoint request, right? And that's how it looks from the forwarding point of view. As you can see, both of the paths, they use different segment IDs or MPLS labels. And this is the last case where this is a use case with layer 3 VPNs, okay? Again, you don't have visibility, that's the case, right? So what happens is now all the domains are isolated, okay? The CPE on the right side, which means the CPE2, now he advertises a prefix X with some specific BGP community. In this case, 100 column 777, right? And we will see why. And once that prefix reaches via BGP to AC1, AC1 will just forward back to the route reflector, and the route reflector will reflect it to the TOR1, right? Because the route reflector is the only device that talks to all of these domains in this case, right? So it will normally now reflect that prefix with that specific BGP community to TOR1, okay? And then what happens is now TOR1 will say, okay, I have that prefix, yeah, but I have a policy on top of that. And that policy is, in this case, LL, right, for that specific prefix. And it can mean many things. It can mean, for example, it can mean low latency path, right? A policy can mean, say, hey, I want to reach a destination, but I need you to calculate for me a low latency path, right? So it goes back now to controller and says, I have that prefix, I have that policy, and that policy can mean everything, and now calculate me a path to reach the destination, which is CPE2 somewhere, based on that BGP community, okay? And then, of course, the answer will come from the PCE controller with this list of segment IDs. So he's pushing now the list of segment IDs back to TOR1, which is based on the constraints, which was the BGP community, right? And then, so the forwarding then will be based on whatever the PC controller was pushing based on the segment IDs, right? So just to summarize, segment routing is meant to be the next generation network transport architecture, right? So it doesn't have nothing to do with services. From services point of view, you still do pseudo wires, layer 2 VPN, layer 3 VPNs, as we did until today. But from the transport point of view, we don't really need anymore to troubleshoot LDP, or we don't need to troubleshoot RSVP anymore. All we need to troubleshoot is the IGP, right? Remember, I guess people who work in the SP environment, you've seen many times, for example, a node failure or a link failure, LDP failure, and that LDP IGP synchronization, then you need to wait some seconds or milliseconds, and then you have some traffic black hole and so on, right? Now here that's not the case anymore, because segment routing protects all the traffic, 100%, with the so-called topology independent LFA. So it uses still the LFA, but it introduces that topology independent case, meaning that it can protect traffic 100%, especially in the, let's say, ring topologies, which is not so easy to have 100% protection with the traditional LFA and FRR, whereas with segment routing, you can do that, okay? Yeah, and traffic engineering with this SR is made simple and flexible. As we saw, you use just a simple controller. You don't need to go to each and every device. You do not need to maintain 10,000 tunnels. Instead, you can have just 10 tunnels with just different, let's say, segment IDs in order to reach the destination. And all of this is being done automatically on top of the PCE controller, okay? It can be distributed or centralized. You can still have your distributed way of IGP, right, distributing the labels, or you can have the controller doing it for you. No state in the network. What it means is now that in case of RSVP, for example, when you created a tunnel end-to-end, now not only the edge devices need to have that state of the tunnel, but all the devices in the middle as well, so the midpoint devices. In segment routing, the state is only minimal, meaning only at the edge device, right? Not anymore at the midpoint devices. And as well, it supports IPv6 as a data plane, as I said in the beginning, specifically for enterprise customers. If you do not want to run, or you're not running MPLS, you can still use IPv6 and do segment routing on top of IPv6 data plane. Okay? Okay, so that was all I had for today. In case you have any questions. Yeah?
I have a question.
Wait a second, please.
Because in all cases, you have the controller on top. What happens should the controller not respond in time, or some disaster event should occur?
Yeah.
Will the devices default to some other state of routing? Will they decide the path by themselves, or what will happen?
Yeah. So if something happens to the controller, you will usually not have one controller. So the recommendation is to at least run two. That's the normal case, right? But anyway, even if the two of them fail, you will still have the forwarding plane running, right? So as long as the forwarding plane is okay, you're fine to go. Now the problem will be if you have a downtime with the controller for a longer time, then that will be a problem, yes, right? But again, we recommend to have a high availability in terms of the controller, and maybe not keep them in the same place, but geographically you can have one at the other side of the world, another one at the other side of the world, so you will always have, reachability between them. But even if the controller fails, from the data plane point of view, you will still be able to forward. The only problem is now that you cannot add new LSPs, unless you want to do it manually, yeah? Okay?
Okay, thank you.
Yeah, nothing.
Have you heard about any big company, by big I mean 500 devices plus, which introduced the segment routing concept in the production network?
Yes, that's. I can show you the documents afterwards.
Okay, can you, if you don't, if you are not able to say what was the name of the company, can you tell something about environment?
Yeah,
Like,
I can tell you in US especially, one of the biggest service providers there. Actually, two of them. Yeah, they are implementing already segment routing. One is running, I think, more than 2 years now. We have in Europe now more than 10 customers, big customers. In 2 of them, I was personally involved. I'm still working on them. And so far, so good. I mean, we haven't seen any issues. So.
Okay, so for them, this solution is stable enough to keep it in production?
Yeah, definitely.
Okay, thank you.
Nothing. Nothing? Okay, thanks then.